traditional custodians of country throughout Australia and their connections to land, sea and community. We pay our respects to elders past and present, and we extend that respect to all Aboriginal and Torres Strait Islander peoples present at this meeting today. Welcome everyone to the first branch meeting for the SSA Canberra branch in 2022. Hopefully everyone's staying safe, and hopefully we have another fun year of data and statistics. So my name is Francis. I'm the current interim president, I guess outgoing president of the Canberra branch of the Statistical Society of Australia. And so just for those who are probably not aware, the SSA is the national body that represents statisticians, data science from all across the country. And if you want to know more about sort of events, workshops, meetings, all that cool stuff that's taking place both nationally and in your local state and or territory, please visit www.statsoc.org.au to find out more. And if you're certainly interested in getting involved and giving back to the statistics and data science community in the ACT and region of New South Wales, then you can contact SSA Canberra at gmail.com. I'm certainly sure that a lot of the branches, in fact, are probably getting close to their annual general meeting, so they're probably all looking for people who want to give back to their community and want to join the council and assist. And so, if you are interested in your own respective wherever you are, please have a look at the StatsOc website and find out a little bit more regarding that. So just a bit of housekeeping before we get things going. So this is an online meeting, and so unless you are speaking, please ensure you mute your audio to try and minimize any feedback and disruptions. Video is entirely up to you. And I guess just to keep things simple, we'll leave questions to the end. If you have any questions at the end, you can, I guess, raise hand or unmute yourself, but you can also post it in the chat, and we'll try to track these things, and we'll let, and obviously Clara will have a chance to look at those as well. Okay, so with that, today it's my great pleasure to introduce Dr. Clara Grazian, who I guess was a senior lecturer at the School of Maths and Stat at New South Wales, but is now at the University of Sydney. So her research interests include Bayesian statistics, mixture models, spatial temporal modeling, copular models, variable selection, and a wide variety of applications in climatology, epidemiology, cybersecurity, and genetics. As an example of that, prior to actually coming to Australia, she was actually a postdoc at the University of Oxford, working on understanding genomic mechanisms conferring resistance to tuberculosis. And so she does really work on a wide range of methodological as well as applied problems. And so today, with that in mind, she's going to be talking to us about a loss-based prior distribution on the number of components of mixture models. Take it away, Clara.
Thank you very much, Francis, for this introduction, and thanks to all the branch for having me, even if just online. I look forward to go to Canberra and visit NAU, hopefully later. So I still consider myself a bit new in Australia because I didn't had the chance to travel much. But I've been here like 3 years. But like part of the work I'm going to present today started before I before I moved to Australia, and the theoretical part was mostly developed while I was already here, but with some collaborators in Europe. And then I will show some applications of that theoretical part that comes from my work on tuberculosis. So I'm going to present some work on mixture models, and most of my research, and in particular this model, the work I'm going to present today, is within a Bayesian framework. So just as like a brief introduction to give the notation, because I'm sure you're aware of this. So the main goal of Bayesian inference is to develop, to derive the posterior distribution of parameters. So parameters are considered unknown quantities, and they can have, their behavior can be described by a distribution. So you define a prior distribution on them, and then through the Bayes theorem, you're able to derive the posterior distribution. So there are several aspects in Bayesian inference that are point of research, because once you derive the posterior distribution, actually in Bayesian inference, you have done everything. and it's just a matter of how to describe this posterior distribution. However, it's not so easy. So the posterior distribution has to be approximated because most of the time it's not available in closed form unless the examples are very easy. Performing model choice may be tricky, and so also variable selection. But one of the main problems is how to select a prior distribution. And this is the main point of criticism most of the times, because it seems like the most subjective part of the analysis. There are cases where the prior distribution has a strong effect. And you would like to understand what this effect is and if it's reasonable in the inference you have. So most of the presentation I'm going to give today is related to the choice of this prior distribution in a particular case. And this particular case is a mixture model. So a mixture model is a combination of distributions where each distribution is weighted with a weight P. So the weights have the standard constraints. They have to be positive and sum to 1. And Fj can be any probability distribution, but it can also, like most of the times, is considered as like the shape of the distribution is the same, and then the only difference between components is the parameters. So there are different distributions with different parameters. So the same form of the distribution, but with different parameters. This is a situation where so these type of models are extremely used because they're very flexible. You can see the classic example of use of these models is can be clustering, where you see each component as a particular cluster, and so the weights represent the proportion of observation belonging to that particular distribution, that particular cluster. But they are more flexible than that because you can describe non-standard distributions as convex combination of distributions, so like very kurtotic, multimodal distributions, etc. So they have been extremely studied in the literature in both a parametric and non-parametric setting, so when k goes to infinity, and in many, like in both theoretical and applied context. The problem with mixture model in a Bayesian framework is how to define a prior distribution. It's been studied that most of the non-informative prior distributions can't be used. When I say non-informative prior distribution, I mean like some prior distribution that are obtained through default techniques. So they are more or less mathematically obtained, but they are not necessarily a proper distribution. So for example, let's suppose that we have for each set of parameters or each component of the mixture model, we use independent improper prior distributions. So this is a distribution which is which doesn't integrate to a constant, so it's not even not normalized. And sometimes they are used in a Bayesian setting because they are considered as limits of proper distributions. So for example, like a classic distribution is a constant over all R for a mean or allocation parameter. And they're usually used because you can obtain the same results as a frequentist or like the symmetric results as a frequentist analysis. So in this case, if you combine this type of prior, the independent improper priors with the likelihood of a mixture model, you can actually augment the mixture model to include also all the allocations, which are unknown as well. So this S is the possible classification of each observation to each component. So it means that if you combine this likelihood, this augmented likelihood with an improper prior, then you will have that the part relative to the distribution associated with the improper prior if there is no allocation of the observation to that particular component, will only, so the posterior distribution of that particular component will only depend on the prior, and if the prior is not proper, then the posterior distribution is not proper, and so inference is not meaningful. So this is an easy example, but actually there are other situations where you can show that by using improper priors, you actually obtain improper posterior distributions, so you can't do that. However, it's also tricky to define a prior distribution, like a subjective prior distribution, so a proper prior distribution, because a mixture model is a sort of inverse problem where you can't associate things that you observe in the sample to specific parameters of the mixture model. And so studying the effect of your prior choices is not so direct as in other contexts. So there are in the literature several priors that have been proposed for mixture models, or sort of objective priors. Most of them are partially proper priors, so they are proper for some of the parameters, but improper for other parameters. In particular, in the 90s, there was some literature based on that. In some other cases, they are data dependent. But of course, like, again, the effect of your choices, if you take some of the parameters to be like fixed in some quantities of the data, it may not be easy to understand their effect. In other cases, researchers use weakly informative priors, for example, normal distributions with a large variance for the location parameters of the distributions. But again, and this may be data dependent or not, but like, again, it's difficult to study a sensitivity analysis on these priors. So I started to work, I just put this in, but I'll go quickly on this. But I started to work on this problem because during my PhD, I was working on the definition of the Jeffreys prior for the parameter of a mixture model. And the Jeffreys prior is defined as the square root of the determinant of the Fisher information matrix. So in this case, we proved that the posterior distribution using this prior, so the prior was improper, but also the posterior distribution was improper for a Gaussian mixture model. But then we used a Jeffreys prior, a conditional Jeffreys prior, only on the weights of the mixture model, and then we partially proper priors on the other parameters, and we obtained a proper posterior distribution, but also with some interesting characteristics. So the idea of the Jeffreys prior for the weights of the mixture has this shape. So this U shape, so it's very concentrated around 0 and 1. And how much it is concentrated depends on the information of that particular component. So for example, if I have a component, so a mixture between two components, one is a normal and one is a student T distribution with different degrees of freedom, I can see that the Jeffreys prior for the weight of the normal distribution is more and more concentrated around 1 with respect to the prior for the weight of the T. The more the T is far from the normal distribution, and is more and more symmetric as the T distribution is closer to a normal distribution. And this means that it favors components which are more informative than the others. And it can be shown also for like two normal distributions, one with a larger variance. And this is a nice property because it may help in identifying the number of components in an overfitted mixture. So if you assume a priori that you have a large number of components because you don't know exactly what is the right number. Like this type of prior allows you to, and this can be like, we prove that analytically, like as the sample size goes to infinity, you can concentrate the posterior distribution on the weights only on those weights of them, only on the weights of the meaningful components. So the posterior distribution of all the other weights, the extra weights of the extra components, goes to 0. So for example, in this data that we assume a mixture model with 10 components, and then the posterior distribution was concentrated not around 0, only for 5 of them. So we could identify a smaller number of components. So this is my past, but then I continue to work in this area. And so in this particular case, the idea was that you still fix the number of components, and then you would like inference to tell you what is the right number of meaningful components. It doesn't necessarily have to be the number of clusters, but like you would like to estimate, to have a model, to have the simplest model, the simplest possible models, so with a fewer number of components, because it's easier to estimate. But you can do it in another way. So instead of fixing the number of components, you can actually put a prior on the number of components and try to understand, try to estimate this extra parameter too. But still, what I liked of what I've shown so far is that there is no so the input of the experimenter is not strong in the definition of the prior distribution, and so you let the data speak more. So I was looking for a prior distribution for the number of components in a mixture model that had this type of characteristic, so that can be used automatically or by default. So the problem here is slightly more complicated because you have an extra parameter, and so you have to define priors for the weights and for the parameter of the components and for K, the number of components. And then you can derive the posterior distribution of K like by integrating out all the other parameters. So you can find the marginal posterior distribution of K and derive it. So there are something to say at this point because like there is some work showing that the prior distribution on K must be proper. So you can't use an improper prior. But another thing is that like even if you think that there is a finite number of components in the model, it is appropriate to define it through all, like on all n, then like all the natural numbers. Because if you truncate the space and you assume, for example, that you want the prior distribution defined on like a compact space between 0, like between 1 and 10 or 30, there is still the possibility that you have some distortion in the posterior distribution, in particular at the boundary. But even if this doesn't happen because you assume a larger number of components, like a very large number of components, this may have an effect in not concentrating the posterior distribution on the right number of components. So like the fact to have like a larger truncation may have some distortion, some bias in the posterior, may lead to some biases in the posterior distribution. And this is associated with the inconsistency that was found in a non-parametric setting. So when you have an infinite number of components and you want to estimate the number of components, so you assume a model with an infinite number of components and you want to estimate that, actually it has been proved that the posterior distribution will concentrate with on a larger number of components as the sample size goes to infinity. So you can't estimate that. So the idea we had was that we would like to, so it's a difficult problem and data may not be extremely informative in this, on this problem. So we would like a prior that gives information. So we would like a prior that penalizes larger or more complex models in order to simplify inference because you have a simpler model and you penalize larger values of k. So we implemented a loss-based approach where we assign a worth to each mixture with k component with a different number of k, and then we include so we define a loss function on which is a function of k, and this loss function has two components, one informative and one like related to the complexity of the model. So about the information loss, we based the definition on the well-known result that if the model is misspecified, the posterior distribution will asymptotically tend to accumulate to the closest model, to the one which is misspecified. And the closeness between these two distributions is given by the Kullback-Leibler divergence. So in terms of mixture, you can think about like different models as different mixture with a different number of components. So you can define the prior for k in terms of information loss through the self-information loss function. So you take the exponential of the loss function, and the loss function is defined in terms of Kullback-Leibler divergence. However, where you consider two different mixtures with a different number of components, for example, like with k components and k+1 components, like you have that the divergence tends to 0 when the two components, so the two models are the same, and the extra component has the same parameters as so you can, for example, you can put the extra parameters to be equal to the parameters of the last component and the weights as well. So like you will have, so sorry, I messed up. So you have that the divergence goes to 0 when the two components are the two mixtures are the same and the extra component has a 0 weight. So the loss, the information loss, actually attains its minimum at 0. So it's not extremely useful in terms of definition of a prior, because then the prior would be improper, and we can't use an improper prior for the number of components. So we can use additionally also a loss relative to the complexity of the model. There are several ways to define the complexity or this loss function. An easy way to do it is to define a linear loss function. And for example, what happens here is that you have a loss that increases linearly with the number of components. This makes sense if you have components with the same number of parameters or like components of the same shape, but only differences in the parameters. So it sort of makes sense to use a linear loss function. However, you can use different types of loss function. And again, you can associate the loss function with the prior through the self-information for some constant c, which is positive. So if you define the prior distribution in this way, we actually prove that you can derive a prior distribution in closed form. In particular, if you augment the problem and you put a prior on C as well, or a transformation of C, and for example, you can put like this is a parameter which is defined. So this P parameter is a parameter which is defined in 0, 1. So you can define a beta prior on that. Then you will have a prior conditional on P, and which is a geometric prior distribution, and the marginal prior distribution for K is a beta negative binomial distribution with shape parameters alpha and beta. So this is also interesting because like the beta negative binomial distribution, of course, is a known distribution, but like we have associated this prior distribution on the number of components with a mathematical derivation. And we have seen that you can actually define it as like a way to penalize the complexity of the model. And you can define this prior distribution in several ways, like it's proper and it's defined on all the support of K, and it has some moments that are have simple expressions. So you can use, for example, alpha and beta both equal to 1 as a default choice. But if you have some prior information, then you can define alpha and beta differently. So it's a bit more, it's easy to use because you can incorporate prior information or you can make some default choices. So what happened is that if we compare the results on the same data set that I showed before for the Jeffreys prior, we used 3 prior distributions. One is this beta negative binomial. One is the Poisson, which is the only other distribution that is available in the literature with a mathematical derivation. And then we use the uniform prior, which is the mostly used prior distribution in this setting, in particular in applied setting. And this, so this plot compares the posterior distributions on the number of components for this galaxy data set. So you can see that the orange one, so the beta negative binomial, is in between the two. The Poisson distribution, so this is a Poisson with a rate parameter equal to 1, and it's very conservative. Other Poisson distribution has been proposed, but you have to choose the parameter, and you have the problem of like expected value and variance which are equal. So this may have an effect on the posterior distribution as well. The uniform prior has the problem that I was talking about before. So it tends to so the posterior distribution when using a uniform prior tends to concentrate to larger values, while the beta negative binomial tends to concentrate around 3, 4, 5 as number of components. More or less in this data set, it's supposed to be between 3 and 6. Like it shows an in-between behavior between a very conservative one and a non-consistent one. And of course, you can change the parameter of the beta negative binomial in order to have like a more conservative effect or a less conservative effect. So this is like the theoretical part, but then I tried to apply this prior on a data set in genomics. So like during my, so I'm trying to show here what is the effect of having a prior which is given by default, so with a limited input by the experimenter, but is more conservative than like a non-parametric model or a parametric model using a uniform prior. So the idea here is that, like I was working, as Francis said, I was working on the analysis of resistance for tuberculosis. And the experiment we ran was checking on a plate several, so like we were inoculating tuberculosis at different level of the drug. So each color represents a different drug. And we were testing where, so at what level of the antibiotic tuberculosis stopped growing. So what was the level of the antibiotic that allowed to stop the growth of the bacterium? And of course, so this is the smaller level of the antibiotic. If it works, it means that the strain is sensitive to that antibiotic. But if you see, for example, for the bedaquiline, which is this drug here, if you see growth everywhere, it means that bedaquiline is not helpful in stopping the growth of the strain. So it means that that strain is resistant to bedaquiline. So this is a standard method to analyze drug resistance of bacteria. And what you obtain is distribution of MICs, which is the minimum inhibitory concentrations of the drug. So for each strain, you have a number, which is the level of the antibiotic, which allows to see no growth of the bacterium. And the data you obtain is like this. So you have full distributions because some strains are resistant and some strains are not. And some strains may show an intermediate level of resistance. So for example, you have cases quite clear. And this is typical of drugs that were developed like early or like some times ago, like for example, rifampicin and rifabutin were developed in the 50s or 60s. So they have strong mechanism of drug resistance. Other drugs are more new, like bedaquiline. So they have a full distribution for the sensitive cases, but they show very few resistant cases. And some drugs like ethambutol and ethionamide or linezolid, they are in between, so they show some resistance, but there are still many cases which are sensitive or susceptible still. And some cases show clear resistant cases, but some cases show like very small, a very small number of resistant cases. So it's pretty difficult to develop an analysis that works for each drug because the type of configuration may be very different from drug to drug. So the idea is to assume a Gaussian mixture model. However, with an unknown number of components. However, the characteristic of this data is that actually data are not continuous, but they are discrete because you just assume, you just see particular dilutions of the drug. So you can just see specific levels of the drugs of the antibiotic, but not the full possible scale of the antibiotic that you can give. So the data are actually discrete. So what I thought to use is instead of using Gaussian distribution, to use rounded Gaussian variables, where the problem can be augmented by considering a latent variable, which is normal. And on that variable, the mixture model is imposed. But then what we observe is a version of this variable, which is limited between the dilutions, so the levels of the antibiotic that we have. So I used 3 methods. I compared 3 methods here. One is EchoFinder, which is a frequentist method, which is the standard method used by the European Health Organization. And in this case, you fix a distribution and then you fix a quantile. and like it's a non-parametric method, but based on the quantile that you fix to study the distribution. So you can see that. So these are breakpoints. So these are separation points defined on the distribution to identify resistant cases from susceptible cases. So you can see that for each drug, like this method, like strongly depend on the quantile that you choose. Then this is a Gaussian mixture model. This is a sensor Gaussian mixture model. That is the model that I just showed. And this is a directly processed mixture model. So it's a non-parametric mixture model, assuming an infinite number of components, but still this is censored. So it's assuming like a censored observation with a latent Gaussian model. So you can see that with sensor Gaussian mixtures, the breakpoints tend to be larger than with the other methods. And this is actually a good point, and I'll go back in a minute, because if I look at the percentage, so I had the information about the strains which are characterized by resistant mutations, in particular for the first-line drugs, so for the oldest drugs. So in this case, I can identify, so usually these numbers are pretty large because these are very well separated drugs. So just going back, you can see that this is rifampicin, isoniazid, and ethambutol. Like this was like the dilutions found in this plate were not correct. So, but like still, you can find the truth. So, like the percentage of correctly classified resistant cases are pretty high for all the methods, except for ethambutol with EcoFinder. But then if I look at the percentages of strains which are correctly classified as susceptible, the numbers can be very low. So it tends to be so with the other methods, it tends to be very easy to find resistant cases, but it's difficult to identify resistant cases, like susceptible cases. So it tends to identify more easily a strain is resistant than as sensitive. So what happens is that this is problematic because like there could be two different situations. One is when there are some intermediate level of resistance. So for example, it's not so easy to say it here, but actually there are cases like in an intermediate level. So if the model is not able to identify those cases as resistant, they may be classified as susceptible, because it's like it may be that like these cases are clearly identified as resistant, but like lower signals are not identified as resistant. And the other case is, for example, for clofazimine or bedaquiline, where I have a full mode and a full distribution for the susceptible cases, but then I have some cases which are less evident. So I have cases here, and I think I have cases here, like for clofazimine, it's a bit more evident. So there is a long tail. There are actually some cases which are resistant already, but it may be difficult for me to identify them as resistant. And this is just the first analysis, because I want to associate those cases those resistant cases with specific mutations conferring resistance to the strain. So if I try to do that with this censored GMM based on the beta negative binomial prior for the number of components, what I can do is actually find most of the known mutation conferring resistance to rifampicin, which are in this gene RPOB. But most of the methods, with all the other methods, where I was not able to identify these green strains, which are associated with RV 2011. And these have been suggested in the literature to be associated with resistance at an intermediate level for rifampicin, but as they haven't been found like from a molecular analysis. So I could clearly see the signal coming from these mutations from the analysis. If I have, if I'm not, like if I have an intermediate level of, so if I can assume that there are more components, and so if I can assume that there is an intermediate level of resistance. And the other case is clofazimine, as I said before. So if I try to find mutations conferring resistance to clofazimine, like what I do is mostly to trying to understand the susceptible distribution. So I'm trying to explain. So if I then use this distribution altogether, and I'm not able to separate between resistant and susceptible cases here, what I'll try to do when I then try to associate this distribution with the mutation is that I'm just explaining the susceptible cases, which show some variability. So there are too many cases, too many mutations that seems to have a correlation with a larger level of MIC. But if I use so like just for those of you who are not familiar with these plots, like on the x-axis I have all the genome and all the possible mutations for like all the possible SNPs, and for each of them I can compute a p-value showing resistance, showing association to the resistance characteristic, and I have the Bonferroni threshold is in red. So you can see that in this case I would see too many signals, like these are like thousands of signals, so it's not very useful to identify mutations conferring resistance to clofazimine. But then if I'm able to separate between like a very tiny level of resistance and a susceptible mode, I am able to identify very few SNPs which seems to be associated. The signal is very low because still I have very few resistant cases with respect to all the other strains which are susceptible. But again, the color ones have been proposed in the literature to be, like in the macrobiology literature, to be associated with resistance to clofazimine. And again, with this method, I am able to see this signal and possibly to identify other mutations. So I am close to an end. Happy to come back to these pictures if they were not so clear. But I just want to conclude saying that like consistently estimating the number of clusters in a Bayesian way is difficult. It's a difficult problem in general because a cluster is not necessarily something that has is a clear definition. So the idea of this method was or this approach was trying to incorporate what you define as a cluster in the analysis, in the definition of a prior for the number of components, but trying to do that in an automatic way so that the experimenter doesn't have to put too much input. And but the prior definitely has an important role and may change the effect of, may change a lot the inference. And it's easy to extend everything I said to the multivariate setting. And that's it. So if you have any question, I'm happy to answer.
Well, thanks, Clara, for a very interesting talk. And I mean, yeah, no, it's really interesting. And I think in a past life, I played a bit with mixture models. And I think what's interesting about this is that I think you've sort of set up a very systematic way of being able to construct a proper a prior for estimating a number of clusters. And then it's interesting, or in a way, it's kind of very nice that it actually comes out to be such a neat closed form to be a beta negative binomial. And it's sort of something that I wouldn't have anticipated, that it's so sort of simple in a way.
Yeah, true. Yeah, we like. I was playing with the loss functions, and like at one point I sort of saw. I thought like I think we can derive a closed form from this, and it ended up as a negative binomial. It's a beta negative binomial. Like the negative binomial has is not as popular as like the Poisson, but there are some authors proposing it. However, there is no without this derivation. So I think it's interesting to see that that particular prior can be defined in this loss based approach, and actually means that you're penalizing the complexity of the model.
Yeah, that's very interesting. Are there any questions for Clara at this point? Again, if you have any questions, you can raise your hand or unmute yourself, or you can put them in the chat. I guess I probably have, well, I guess I have a couple of questions, but the first one is probably the simple one, is, I guess the simpler one, which is sort of, how do you actually, is this done through MCMC, like a reversible jump MCMC, or is this actually done through so how does the computation go for these things?
Yeah, so there are two possible ways to do it. Definitely reversible jump, and I did both. So one is a reversible jump. The other one is there is actually recent work showing that there is a parallelism between the non-parametric mixture model and a finite mixture model. And you can actually use the algorithms developed for non-parametric model mixtures, also for finite mixtures. And so this is usually more efficient using, yeah, like they're based on stick breaking constructions, so they're usually more efficient. So you can do that, and it's definitely more efficient, and it mixes better than reversible jump.
Okay. Oh, okay. Cool. I guess another question I had is, you mentioned one of the tables before with the breakpoints.
Yeah.
You mentioned that basically the censored Gaussian mixture model tends to produce higher breakpoints. I was wondering, is that kind of a consistent trend, that because of the actual underlying methodology with the censoring, that it tends to produce higher breakpoints? Is that something that's sort of like, what's an intuition behind that?
So censoring, so I didn't write censoring here, but like this Dirichlet process is also censored. So I think there are two points, and one is that if you don't use that, if you don't, so like this GM, so this Gaussian model doesn't use censoring. So definitely it tends to be smaller, because it identified is like, since like the variable is supposed to be Gaussian while it is not, it may identify more modes or more components than it should. And so this is something that is missing. And so like this is why they are so low. So the censoring helps with that. But on the other hand, like this model is comparable to the case of using a uniform. So it's not exactly the same, but like it's comparable to the case where you use uniform prior. And in this case, what happens is that, again, you tend to have more. So while this censor Gaussian mixture use the beta negative binomial prior, and so you tend to estimate more components, and it means that if you're trying to separate, like you will separate probably the susceptible cases between groups. And so what you are trying to do after is to explain also differences between the susceptible cases, while using a more conservative prior separates more between the group of susceptible together and different groups of resistant cases. So like I think using both like censoring and a conservative prior may help
okay.
in identifying that.
Oh, okay. Oh, okay. Okay. Are there any other questions or comments that people would like to make? Anton.
Sure. Yeah. Really nice talk. One thing I didn't get, so after you do that bit of modeling, right, and then you try to go to the specific genes, right? Did you fit as like one full model, or you did it separately?
Okay, so when I associate, so what I did, so going from this, yeah, I didn't say that. So what I did, I was a bit too quick here. So is to identify the clusters with this model. So like, so I was estimating this model, like the sensor one, and I was identifying and allocating each strain to a specific cluster. And then I did a GWAS, so like a regression models for the like, it depends on the drug, but like possibly 2 or 3 levels of resistance as outcome. And so I was associating that with, I was associating the classification with all the possible mutations, if it makes sense.
Yeah, that makes sense. Do you think you could just put that all in one model in some sense, right? To kind of fully bring the uncertainty through?
Oh yeah. You can embed I mean, this is a problem of variable selection, and you can embed that while you're doing clustering. Yes.
Yeah, thank you.
It's a bit more. So the reason why I didn't do it is that I was using more efficient algorithms for the variable selection for the regression. So I didn't embed them within the clustering, which was lower. So there is, but possibly it is possible. Like it is possible to do it more efficiently together, definitely. So yeah, it is possible.
Thank you.
Thank you.
Thanks, Anton. Any other final comments or questions for Clara? Okay, I don't see anything else. So if not, let's thank Clara again for a very interesting talk. So thank you, Clara.
Thank you very much for inviting me.